All right, everyone. Oh, I'm going through it, brother. Let me tell you, I am going through it. Just moved, new place. Listen, I've been crazy busy, so we're going to be playing this one all off the cuff, all by ear. It's going to be a little bit scuffed, but listen, that's how I run it. Listen, you can see the ideal male living space behind me. I got the bass guitar. Oh, you know a brother got a mattress just on the floor, no bed frame. And oh man, I think you can even see the dirty clothes. Let's see if I turn around. Yeah, you can even see the dirty clothes in my closet, so you know we out here. Yeah, it's going to be a rough one this week, so stay tuned for that. All right, let's get into it. What are we learning about today? Well, today we're learning about linear regression. Listen, you might not know it by this name, but you've been using this forever. It haunted your dreams all the way back in good old algebra back in high school when people like me were busy getting shoved into lockers and given swirlies. If you think you don't know what it is, you probably recognize this, right? Y equals mx plus b. It's a classic. This is the simplest way to denote linear regression. Now, we have this formula, right? But what actually is linear regression? Well, it's basically just an attempt to predict some value, right? We have as y, and that value is going to be predicted using a couple things, right? It's going to have some input variables we'll call x, right? And also, there's going to be some value that y starts out as. When x is 0, we call this the y-intercept, and it's denoted by this b. And then we're basically just trying to find the weights. They're called coefficients officially, but these values here, this modifier on our input variables that best predict y when you add the y-intercept to it, right? That's all this is. And so converted into machine learning form, what we have here is a new equation, right? And this is our prediction, or the prediction our model is going to make. And that's just equal to our input features, right? The data we feed into the model multiplied by a vector of weights plus some inherent bias in the model. This is all it really is, right? And so we can take your simple little algebra 2 equation and turn it into a very simple and fundamental machine learning model right here. And when do we actually use linear regression? Well, we need linear, all numerical predictions, right? So like an example would be, let's say after the singularity has emerged, most humans are completely eliminated. We want to predict the number of trash cubes that I can scavenge to use as currency in a given region. Well, this might depend on several features. For example, the number of kilotrons patrolling the area for humans, and of course the distance from the human harvesting facility. They'll be using us like batteries, just like in the Matrix. And you can make a couple of like little predictions. For example, the higher the number of kilotrons, maybe, there's lots of trash cubes left around because there aren't many people left. And the distance from the human harvesting facility, well, there might be tons of trash because the robots, people stay away from the human harvesting facility. So we can see that these features scale linearly with our number of trash cubes in a region. This is the perfect type of problem to use linear regression on. For a slightly more practical example, right, just to make this a little more clear, we might actually have something like the number of cores in your CPU and the amount of VRAM in your graphics card, and maybe our output could be the price of a computer, right? That's your simple, no fun model, but I prefer this one. So to take what we just learned, our actual mathematical formula, and then apply it to the example I gave with the number of trash cubes, we're going to have a model that looks something like this. So what we basically have here is we have our prediction, right? Our number of trash cubes, right? And then we have a tensor, right? In this tensor, each column corresponds to a feature. So we have our distance in this column, and then we have our number of kilotrons in this column, and that's our features right there. We then multiply that by our weights, which are right here, and then we add our bias. So you can kind of see how this is represented using tensors and using some linear algebra with the matrix vector product of this matrix here and this vector here. That's all this is. Now, what is our actual goal here? When we train our model, what do we want it to actually do? It's actually pretty simple. We want to keep training our model and adjust those weights and those biases so that we have the best weights and biases possible, and therefore our model makes the best predictions. So when we have weights and biases determined that most accurately predict what we're actually trying to predict, That's how we know our model is correct. So once we've updated our weights, our biases, and are ready to make a prediction, how do we measure the performance of our model? Well, we use what's called a loss function, which I'll probably make a video about at some point in the future, but they're basically a way of measuring our distance from our model's predictions to, its actual values using something like a test set or a training set. And the most common loss function used for linear regression specifically is what's called the mean squared error. Basically, all it is it takes our prediction, it then compares that to some kind of actual value, takes the distance between those and squares it, divides it by 2, and then you sum that up for everything in your training/test set, right? So it's just your averaged, so it's literally just your average squared error, right? We have this part, the squared error, then we take the mean. What we can do is we can use the value that this gives us and attempt to minimize it, which gives us an indicator of how close or how optimized our model actually is. And finally, one thing that makes linear regression so interesting is that it actually can be modeled as a very simple neural network with a number of inputs, for example, our features. So we could have like our number of kilotrons and distance from the human harvesting plant as our features, right, or inputs. And we have a bunch of different inputs, all of which are directly connected to an output neuron. So we have a bunch of input neurons and a bunch of output neurons, even in something like linear regression, making this a very, very, very simple linear model. Now, if you watched my videos on multilayer perceptrons, which if you haven't, you should, I'll put a link up here somewhere, you might notice that this is an example of a single layer perceptron. Now, obviously this is linear regression. Multilayer perceptrons are usually used to add elements of non-linearity to model more complex problems. But this is basically the direct precursor to a multilayer perceptron and one of the fundamental building blocks from which the rest of the machine learning field is derived from. So this is just a super interesting foundational point for the machine learning field. Thank you so much for watching another episode. And if you want more information, you can check out my GitHub, github.com/chrishugh, as well as my Substack. I actually just published on both of these a new project where I attempt to get Llama 2 running on GitHub Action Runners for free compute. I might be making a video about it in the future. If so, I will link it here. So note to future Joe, if you do it, remember to watch this video and add this in. But listen, thank you so much. Please check out all the rest of my content. Like and subscribe if you got anything from the video, if you learned something new. And yeah, I hope to see you very soon for more MLAI content that you know and love. Thank you so much for watching and have a great day.